Okay, in this section I'm going to talk about basic differentiation rules, and then we'll talk a little bit about rates of change. The basic rules for differentiation, you'll love these rules after using the definition of the derivative, but you better master these rules of differentiation because you're going to have to use them. As long as you're in calculus, you're going to use these rules. They're not going to go away. So you need to memorize them and learn how to use them. Okay, the first rule is the constant rule, and it basically says the derivative of a constant is always zero. Now, if your instructor, requires that you prove these rules using the definition of the derivative, then that's going to be a different, that's going to be a problem for you, because I'm not going to prove these rules in this lecture. So I'm just going to show you examples. So if your function is a constant function like 5, then the derivative of that is going to be 0. Also, if your function is pi, then the derivative of that function is going to be 0. So as long as the function is a constant, the derivative is always 0. And I can kind of explain that to you because remember, the derivative represents the slope of the tangent line. And if you think about a constant function, it's just a horizontal line. So think about what would the slope of this horizontal line be at any point on it. Well, the slope of this line is always 0. So that means that if you took the derivative of a constant, you would always get 0. Now, one of the favorite rules is the simple power rule. There's a general power rule we'll talk about later. But the simple power rule, it says, what if you want to differentiate x to the n with respect to x? Well, the rule is pretty simple. You just bring down the exponent n, and then you multiply it by x to the n minus 1. In other words, you reduce the exponent by 1. So an example of that would be if you want the derivative of x to the 7th, okay, well that derivative would be 7 times x to the 7 minus 1, or 7x to the 6th. Now, something like that you can probably do in your head with practice and just skip this middle step. Now, one of the things that you have to do sometimes, especially on radicals and rational exponents, is you have to be able to rewrite an expression with an exponent. So if I have the 5th root of x squared, you better know how to write that as x to the 2/5 power so that you can differentiate that function. Once you've rewritten it, then you can take the derivative using the power rule. So remember the power rule, you bring the power down, so I bring the 2/5 down as a factor, and then I reduce the power by 1, so 2/5 minus 1 is going to be negative 3/5. So I'm going to have 2/5 times x to the negative 3/5. And most instructors ask you to rewrite your final answer without negative exponents. So we would rewrite this as 2 over 5 x to the positive 3/5. Okay, here's another one. The function 1 over square root of, 1 over cube root of x squared is actually the same as 1 over x to the 2/3 power. Well, that can be written as x to the negative 2/3, and now that I've written it like that, I can use the power rule. So using the power rule, I bring the negative 2/3 down as a factor, and then I subtract 1 from the power, and then I get negative 2/3 times x to the negative 5/3, and then to get rid of my negative exponent, I move x to the 5/3 onto the bottom, and so I get negative 2 over 3x to the 5/3. Now, a special case of this is that the derivative of x is 1. And you can show this with the power rule, because if you take the derivative of x to the first, well, the derivative of that would be 1x to the 0. And of course, x to the 0 is just 1, so 1 times 1 is 1. So the derivative of x with respect to x is 1. There's also a constant multiple rule, and when I show you these rules, it actually is what allows you to skip some steps. So here, the derivative of a constant times a function is actually the constant times the derivative of a function. So basically, if I want to find the derivative of 7x cubed. And what I should have done here is shown you the intermediate step. So the derivative of 7x cubed would actually be, that derivative would actually be 7 times the derivative of x cubed. So what's the derivative of x cubed? It's 3x squared. So, and then 7 times 3x squared gives me 21x squared. But see, with practice, you don't need this intermediate step. You can actually just do this in your head. The derivative of 7x cubed is 7 times the derivative of x cubed, so that would be 7 times 3x squared, which gives you 21x squared. Now this one I actually did show you. If I want to find the derivative of 5x to the 1/4, then that's going to be 5 times the derivative of x to the 1/4. Now, this right here is not actually applying a derivative. It's actually showing you what I'm going to do next. So what I'm going to do next is just telling you that I'm going to take the derivative of x to the 1/4. So my answer is going to be 5 times the derivative of x to the 1/4. And then here I'm actually going to get the derivative of x to the 1/4. Using the power rule, the derivative of x to the 1/4 is 1/4 x to the negative 3/4. And then you can move x to the negative 3/4 to the bottom and write it as x to the positive 3/4, and then 5 would be in the numerator and 4 would be in the denominator. So that would be your final answer. And actually, you can do the rules in your head, like I said. Like if you want to find the derivative of 5x to the negative 7, well, you can say in your head, well, that's 5 times the derivative of x to the negative 7, so that would be 5 times negative 7 x to the negative 8, which would give me negative 35 x to the negative 8. Now, I don't propose you skipping steps unless you feel very comfortable doing so. And then finally, you can write negative 35 x to the negative 8 as negative 35 over x to the 8. There's also a rule for the sum. So this is actually two rules in one. The derivative of the sum of two functions is the sum of the derivatives of the two functions. And also, if you have the derivative of the difference of two functions, that's the difference of the two derivatives. So basically, it basically just means that if you have several functions added or subtracted together, then you can just differentiate them term by term. So for instance, if I have 5x to the 4th minus 3x squared plus 7x minus 1, now I didn't write out that I was going to take the derivative of this minus the derivative of this plus the derivative of this minus the derivative of this, but I just went ahead and did it. So to get the answer, I know I can take the derivative of each of these four terms. So that's all I'm going to do. So the derivative of this function is the derivative of the first term, which would be 20x cubed, minus the derivative of the second term, and the derivative of 3x squared would be 6x, plus the derivative of 7x. Well, the derivative of 7x would be 7 times the derivative of x, and the derivative of x is 1, so that's just going to be 7. And then, of course, the derivative of the constant is 0. So your derivative is 20x cubed minus 6x plus 7. Now, if it's a little more complicated, you might actually show the rules. Here I have square root of x plus 4x to the 5th. So if I want to find the derivative of this, I need to write square root of x as x to a power. So I wrote it as x to the 1/2 power. So the derivative of this sum is actually the derivative of the first term plus the derivative of the second term. And again, this is just showing you that I'm going to take the derivative of each term. So the derivative of x to the 1/2, use the power rule, you get 1/2 x to the negative 1/2. And then the derivative of 4x to the 5th, we can use the constant multiple rule and the power rule together, and we get 4 times 5x to the 4th. And so now 1/2 x to the negative 1/2 is the same as 1 over 2 times x to the 1/2, and 4 times 5x to the 4th is 20x to the 4th. And here's another one, 5 over x to the 2/3. Notice I wrote that as 5x to the negative 2/3. Then I have minus 3x squared plus 5. Well, I need to take the derivative of each of those terms. Okay, now here I kind of skipped a little bit of the steps, but I'll let you figure out. if I take the derivative of this, I'll actually get negative 10/3 x to the negative 5/3, and if I simplify it, it'll be negative 10 over 3x to the 5/3. This one's easy. If you take the derivative of 3x squared, you get 6x, so that's just going to be minus 6x, and of course the derivative of this constant is 0. Now here's a couple more problems that you can try. Here's a polynomial that you can try, and your answer is given over here. And then here's a strange, kind of a long strange function that you can try, and the answer is actually given over here. You might notice I did some of the legwork here and actually wrote the exponents in a nicer form for you. But you need to be able to do this. You need to be able to convert this to this form before you differentiate. To find the derivative of trig functions, I'm going to show you one, and then I'll let you worry about the rest. The derivative of sine x is actually cosine x, but let me show you how you can get that. But you have to use the definition of the derivative. So the definition of the derivative would mean that I take the limit of sine evaluated at x plus delta x minus sine x all over delta x as delta x approaches 0. So this is just going back to the definition of the derivative for the function sine x. Now, what's interesting is sine of a sum, sine of x plus delta x, there's actually an identity for that. That can be written as sine x cosine delta x plus cosine x sine delta x. So you can look up that identity. So I'm going to replace that sine x plus delta x with this expression here. And then what I'm going to do is I'm going to take the cosine x and the sine delta x, and I'm going to write it here. And then the sine x cosine delta x, I'm going to put it here. And then the minus sine x is going to be here. And there's a reason I'm going to do that. Because in these two terms, I can actually factor out a sine x out of this and get cosine delta x minus 1. So now, if I can break this up into two terms, this would be the limit of cosine x sine delta x over delta x, which is this, and then it can be the limit of sine x cosine delta x minus 1 over delta x. Okay, well, here's what happens here. The cosine x does not depend on delta x, so that's just going to be cosine x, and then you're going to have the limit of sine delta x over delta x as delta x goes to 0. Well, you might remember that limit there we said that the limit of sine x over x as x approaches 0 is 1. So that limit is just going to be 1. And then over here, again, sine x is not dependent on delta x, so the limit of sine x is just sine x. And then this is cosine delta x minus 1 over delta x. Well, it turns out that you can easily show, I think the limit we had was the limit of 1 minus cosine x over x as delta x goes to 0. But this is just the opposite of that because the numerator is turned around. So the opposite of 0 is simply 0. So this limit's just going to be 0. So you end up with sine x times 0. So cosine x times 1 plus sine x times 0 is simply cosine x. So using the definition of derivative, I've shown you that the derivative of sine x is cosine x. Similarly, you could show that the derivative of cosine x is actually minus sine x. And so here's the table of your derivatives. Sine x, the derivative is cosine x. For cosine x, the derivative is minus sine x. For tangent x, the derivative is secant squared x. For secant x, it's secant x tangent x. For cosecant x, it's minus cosecant x. Actually, that should say cotangent. It's minus cosecant cotangent x. And then for cotangent, it's minus cosecant squared x is the derivative. So all of these can be proved either using the definition of the derivative or applying some rules that we'll get to later. So in the next video, I'll talk a little bit about rate of change, and then we'll be finished with this section.